Another example on the Thomson experiment, working with a different particle now. Now we have an alpha particle passing undeflected through perpendicular electric and magnetic fields. If the magnetic field strength is 4.50 times 10 to the negative 2 Tesla, alpha particle is accelerated through a potential difference 4.12 times 10 to the 3 volts. We're looking for the strength of the electric field. Again, write down what you have. You're looking for electric field. You have the voltage that's accelerating this, 4.12 times 10 to the 3 volts. You have the magnetic field strength, 4.50 times 10 to the negative 2 Tesla. And we know it's an alpha particle, so I'm just going to write down the charge. It's 2 times the elementary charge, which is off my data sheet. And I also know the mass, which is off my data sheet, right at the top right on your sheet, 6.65 times 10 to the negative 27 kilograms. So that's all the information I have. If I know it's passing undeflected through these two fields, that means that the electric force is going to balance with the magnetic force. And again, we know the formulas for these. These are QE equal to QVB. So we want to work with this formula. We want to solve this for electric field. That's what we're trying to find here. So the electric field, again, the charge divides out, is going to be equal to the velocity times the magnetic field strength. Now, unfortunately, I don't have velocity in this case. But if you're ever given the voltage it accelerated, you know the potential energy would be gained through the voltage. That converts to kinetic energy, which is the velocity. So you have a conservation of energy formula that we worked with way back when in Unit 2, that the potential energy QV is going to be converted to kinetic energy 1/2 mv squared. So we could manipulate this for velocity. We know the mass, we know the charge, we know the voltage. So it's going to be, you might remember this formula now, 2QV divided by m equals v squared. So V is going to equal to 2Q potential difference divided by mass square root. I could work these out individually. I always choose just to create one formula if possible. Since V is just going to substitute into the other equation, I'm just going to write this as substitute equation 2 into 1, and we get this fancy equation for the electric field is going to be equal to the velocity, which is 2 times the charge times the voltage divided by the mass square root times the magnetic field strength. Put those numbers in. Lots of numbers to work with. 2 times the charge turns out to be 3.20 times 10 to the negative 19 coulombs. The voltage turns out to be 4.12 times 10 to the 3 volts divided by the mass of the alpha particle, 6.65 times 10 to the negative 27 kilograms. Take the square root and then multiply that whole answer by 4.50 times 10 to the negative 2 Tesla. Should be able to punch this in 2 parts. I would probably just work out what's in the square root first. So 2 times 3.2 to the exponent negative 19 times 4.12 to the exponent 3 divide by 6.65 to the exponent negative 27. Take the square root of that answer. Then multiply by 4.5 to the exponent negative 2. And you end up with an electric field strength here. When we go to the significant digits, 3 significant digits, should be 2.1, 2, 3, 4. I get 2.83 times 10 to the 4 newtons per coulomb. So when you punch all that in, should get 2.83 times 10 to the 4 newtons per coulomb. This again is another very common type of question. You might remember after me going through a few of these steps. Similar in example 1, electric force equaled magnetic force when we passed through undeflected. But in this case we were given a voltage, and from the voltage we had to think conservation of energy. Potential energy between the plates, QV, converts to kinetic, 1/2 mv squared. So whenever you're given voltage, you can find velocity and vice versa by using that conservation of energy formula.